next time onwards, we'll keep the session in the evening itself. Okay, that would be better. Now, I just have some queries I would like to ask all of you. Would you like to take a test on MCQ questions which come in the interview and practice on it?
Yes.
If yes, just drop a message. So what I will do is I'll create a test for you guys. I'll share the link with Rahul sir. He would in turn share the link to all of you. You can take a test on it. This test is purely to verify how much knowledge you have and to understand yourself that how much you need to work more. Okay, this is not like somebody will give you a Nobel Prize if you come first rank, or if you fail somebody will throw you out. It's nothing like that. It's purely practicing purpose. Okay, so I'll create a certain tests, one or two tests for you guys. I'll share the link with Rahul sir, so you can practice with on those questions, right, which might help you for your interviews. Okay. And in any of the questions, right, in any of the questions, if you are not able to understand, right, you can message me those questions. I'll help you out to understand, right, those questions. You can ping me on the WhatsApp. I'll explain those questions along with the answers, how that needs to be solved. Okay. Chalo. Now today, we'll start working on the trapping rainwater problem, right? So first of all, we need to understand what is a trapping rainwater. I think last time we didn't start that because of time constraint, but today we'll finish off with that as well. Trapping rainwater problem. Okay. So first of all, we need to understand what the problem is about, right? I'll draw a pictorial representation so that you can understand it better. So that you can understand it better. Okay. So let's draw here. Let's take a sample input. Trapping rain water. This is a quite simple example. Okay. And most appearing question also. But what will happen here? They have given the question name as trapping rainwater, or they might come up with a different name or different story. But the purpose of this question will be similar. The base of the problem will be similar. Okay. So let's take an array here, ARR. This array contains, okay, this array contains certain number of elements, 3, 0, 1, 0, 4, 0, and 2. These are the number of elements we have. Now, what we need to do is, right here in this problem, first let us draw a graph here, which will help us to understand. Okay. Okay. So let's see here. First of all, right, here the first element is 3. The first element is 3. So what we will do is we'll draw a bar of height 3. We'll draw a bar of height 3. This side, it will be an elevation, right? Elevation map. Okay. And the second element is 0. This is the first element, 3. And the second element is 0. Second element is 0. So now we will go with the third element. Third element is 1. So the elevation will be only by one step. The fourth element is 0. Now fifth element is elevation is 4. So we will draw the 4 elevation, and the sixth one is 0 again, and the last one is 2. Okay, last one is 2. Now if you look at this picture, right? Okay, if you look at this picture, one second, you can just highlight it so that you can understand it better. Okay, so wherever we have marked this will be the solid part or the building material, whatever you can call. Now you need to find out how much of rainwater can be trapped inside this. This is all rainwater, right? This is what is all about rainwater. Okay. Now you can start counting how much of rainwater can be trapped here. Now you will get to know, yeah, right? You will get to know how much of rainwater can be trapped. So you start how much blocks of rainwater can be trapped here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So your output should be 10. So this is the task given in this problem. Okay, this is the task that is given in the problem. Now you need to first understand, right, different observations here, right? We need to understand the different observations here. Okay, now first thing, right? Okay, so first of all, an element of an array can store water if they are having higher bars on the left side or right side. See, for example, if you look at this one, if it has a higher bar on the left side and higher bar on the right side, then only it can store a water. Okay, then only it can store a water. Now, observe this border part. Now, if you look at the border part, I cannot store water on this side or I cannot store water on this side. So we need to calculate it only from this element to this element. Means from the second element to the last but one element. Only for these elements, right? For these elements, we need to find how much of water can be trapped, because the first and last element will act as a border. First and last element will act as a border. So we need to observe here, right? First of all, you can write the first point as, okay, water can be stored. Water can be stored if there are higher bars on left and right side. Higher bars on the left and right side. That is the first observation that we need to keep in mind. Okay, so how we can find the water accumulated there, right? Water stored, right? Water stored in every position, right, can be found by finding the heights of higher bars on left and right. So based on that higher bars on the left and right side, we can find how much of water can be accumulated there, right? So total water, right, stored is equal to summation of water stored at each index, right? Okay. Now, no water can be stored if there is no boundary on both sides. You cannot store a water if there is no boundary on the both sides. Halima, please mute yourself. I think Karka. Okay. See here, if you look at this index, we don't have a left side and right side. We don't have a higher bars than this. So we cannot store a water at this position, right? We cannot store a water at this position. So this index does not have a boundary. Okay. Now let's go with a method one, how we can solve it, right? So let's go with a method one, right? Let's go with a method one. Let me copy and paste that. Let's take it up here. Okay, we'll start working on this. Now, let's start with the method one. What we will be doing here is, okay, for each index, right? For each index, starting from where? Each index from 1 to n minus 2. From this index till this index, right? Till this point, right? Starting from index 1 to index, right? N minus 2. What we will do is, right? First one, we will find maximum element on left side, right? And find maximum element on right side. Means biggest element on the left. See, suppose if I start with this position, currently it is 0. So whichever is the biggest element on the left side of it, right? Left side of it as well as right side of it, whichever is the biggest element. We will keep a track of that. Once you get these two, right? For example, let's say currently we are working with a element 0, ARR of 1. We are working with this one. So what is the current element? It is 0. Okay. Now what is the biggest element on the left side? It is 3. Biggest element on the right side is how much? It is 4. Now, right? Okay. Biggest element on the left side is 3. Biggest element on the right side is 4. So how much of water can be trapped, that can be identified using this. Now how we can calculate this, right? So now result can be calculated, right? Based on if left is less than right. If left is less than right, okay, then we will consider, if it is true, we will consider left minus ARR of I. If it is false, we will consider right minus ARR of I. So in short, whichever is the smallest height, that needs to be considered, right? Choose the smallest height. Choose smallest height. Choose smallest height. You have to choose the smallest height minus the current element. That will give us the amount of water that can be trapped. So as of now, left is smaller than right. So right, left is smaller than right. Condition is true. 3 minus 0 is equal to 3. So you can find out how much of water can be trapped there. Right? You can observe here. We can trap almost here. You can see 1, 1, 2, and 3. So we can store 3 height. Elevation will be of 3. 3 blocks of water. That can be found out with this method. So like that, we will do it for every element. We will do it for every element till here. Right? And we'll keep on adding all the values what we get. This will give us the total amount of water that can be trapped between these places. Are you able to understand? Is everybody able to understand how much of water can be trapped in this? It can be found by finding the biggest element on the left side, biggest element on the right side, and you need to find the difference. Choose the smallest height minus the current element. That will give us the water that can be accumulated in that place. Are you able to understand? Please do acknowledge. If yes, then we'll start the implementation.
So is it like the first biggest after the eye or from the last first biggest?
See, you choose the current element. This is my current element, index 1. Okay, what is the index 1 element in the array? It is 0. Okay, so choose the biggest element on the left side. Choose the biggest element on the right side. So biggest element on the left side is how much? It is 3. Biggest element is 4. Now we need to consider the smallest height here for this element. If you are, if it is too much written there, 1 second. For this height, we need to consider the smallest height. Why we have to consider smallest height is because, see, you cannot keep water at this level because it will overflow from this side. So we need to choose the smallest height minus the current value, minus the current value or current position. It will give you the amount of water trapped here in that current position. Are you understanding? Now at this position it is 3. Now you go for the next element. Next element is what? 1. So biggest element is 3 on the left side. Biggest element on the right side is 4 for 1. So which is the smallest? 3. 3 minus 1 is 2. So you can trap 2 height of water. I'll explain it one more time. I'll draw that image again. I'll explain it one more time. Okay, just observe here. See, I'll write down the array element also so that you will understand easily. Comparison becomes easy. 3, 0, 1, 4, 0, and 2. So we need to traverse from this element to this element. Only for these elements we need to traverse. Now you will run a loop starting from this element. So currently ARR of I is what? It is 0. I think 3010. Yeah, I missed one element. 3010402. Thanks, Akash. Okay. Now the current element is 0. Find the biggest element on the left side for this 0. What is the biggest element on the left side here? Biggest element
Four,
on the
four sir.
left side,
3.
3. Which is the biggest element on the right side of that 0?
4 sir.
Okay. Now, what will happen here is For this element, biggest height is this left side. Biggest height on the right side is this. Okay. Now, I I cannot choose the biggest height as water accumulated, because if I consider, can you see here whether water will stay here? No, it will not stay because it will overflow from this side. So we need to consider only the smallest height. We need to consider only the smallest height out of these two. Whichever is the smallest on left and right, consider that. So currently, what is the smallest? It is 3 minus current position element 0. So the result what you get is 3. That means you are able to accumulate 3 blocks of water in that position. Are you getting 3 blocks of elements? Now we will repeat this step for the next element also. So assume that the next element ARR of I is 1. This is my current element. Okay. We are doing it for this. Okay. Now, what is the biggest element on the left side? It is 3. Biggest element on the right side is 4. Right. For this one. Now, how much of amount water can be considered? You need to consider the smallest among left and right. It is 3 minus 1, which is equal to 2. Now, if you look at here, you can accumulate 2 blocks of water.
Also question is rainwater violation.
Are you able to understand?
Yes, sir.
Yes.
Yes, sir.
Clear? Now, similarly, if you go for the next element, let's do it for one more element, ARR of 0. Next element. Sorry, ARR of I, next element is 0. Okay. For this one, currently we are working with this element. So biggest element on the left is 3. Biggest element on the right is 4. Right? Choose the smallest one, 3 minus current element, which gives you 3. So you can accumulate 3 blocks of water in that. Now try for the this one, right? The current element ARR of I is equal to 4. Now, do we have a biggest element than the current element on the left side? Do we have a biggest element, current element?
No, sir.
No,
We'll
right?
just move forward.
So obviously, we will move forward because you cannot accumulate water. There is no bigger element on the left side, right? Bigger element on the right side. No bigger element. So you cannot accumulate water. So what will happen in this situation is, right? 4 minus 4, again 0. There is no water can be accumulated. Now for the next element. For the next element, again it is 0. Right? Again it is 0, current element. Okay. For the next element, again it is 0. Now on the left side, which is the biggest element? 4. On the right side, which is the biggest element? It is 2. Right? Now whichever is the smallest, 2. 2 minus 0. So this is the result I've got. So 2 blocks of water can be stored. Now what you can do now is add this number 2 plus add this number 3 plus add this number plus 3 plus add this number 2. Total is equal to 10. Is everybody understanding this?
Yes, sir.
Okay. So
So we can.
now, tell me.
I was just thinking about the code.
Okay. Can we implement it now?
Yes, sir.
We'll use C for implementation.
Yes, sir. Fine.
Okay. Okay. So first, let's declare an array here. Int arr of, we will take the same array, what you call, which was chosen there, 3 comma 0 comma 1 comma 0 comma 4 comma 0 comma 2. Okay, this was the array. Let's find the number of elements. N is equal to size of arr of 0. Sorry, size of arr divided by size of arr of 0. Size of the array divided by size of the first element. That will give us the number of elements. Now print f, right? Okay. Stored water is equal to %d double quote comma. Now, right? Okay. Rain water. Let's call a function called as rainwater, and we need to pass the array and number of elements. So we are calling a function called as rainwater, right? This function will find out the total amount of water that can be accumulated, and it will return the sum of it. Okay. So return type of the function is int rainwater, and the first parameter is array. Second parameter is number of elements. Okay. So I need one variable to store the result. Initially, we'll keep it as 0. Okay. And I need one variable to keep a track of, right? To keep a track of biggest element on the left side. And one variable to keep a track of the biggest element on the right side. Now, as we have discussed, we need to run a loop from which element? Second element to the last but one element. Second element, right? And till the last element. So my loop will become I is equal to 1, I less than n minus 1, and I plus plus. Inside this, the first step is what? Find biggest element on left side. So what I will do is, I will assume the current element as the biggest element. So left is equal to arr of I. Left is equal to arr of I. I will assume that. And traverse the array. For j is equal to 0, j less than I, j plus plus. Okay. So this will help me to find the biggest element on the left side. So what I will do inside this, if arr of j is greater than left, then the left will be equal to arr of j. So this will help me to find the biggest element on the left side. Okay. Next, find biggest element on right side. Okay. Now, so similarly, we follow the same pattern. I will assume the current element as biggest element. Then I'll traverse on the right side. So right side indexing will start from where? It will start from j is equal to I plus 1 till the last but one element, n minus, sorry, till the last element, j plus plus. Inside this, I'll compare. If arr of j is greater than right, then I'll change the right for the biggest value. Okay. So once you get both of these, next what we have to do, right? Res is equal to res plus. So we have to choose whichever is the smallest. So what I will do, left smaller than right, question mark left, colon right. So if condition is true, left will be assumed. Condition is true, left will be assumed. Okay. If condition is false, right will be assumed minus the current element. Minus the current element. Once you calculate this for each element, then return the result. That's it. Is everybody able to understand? Are you guys able?
Yes, sir.
Okay, very good, very good. Okay, so this is a very basic method. You know what is the problem occurring here? Loop inside a loop. The time complexity of this will be, right, O of n square. That is the problem with this logic. Now let's check the result. See, stored water is 10. Stored water is 10. Right? So we're getting a correct result. So what I'll do is, I'll take this and keep this here as a solution. I'll keep it in this notepad itself so that it becomes easy for you to follow it up. Any doubts with this question in the basic method? If you have any doubts, you can ask. If no, right? So time complexity of this will be time complexity of this will be O of n into n. That is n square. I cannot type n square there. So that's why I've written O n into n. This is very basic method. If you are looking at auxiliary space means extra variable, that is O of 1. The extra space that we use is, right? Sorry, not O of n. Space complexity, right? Every time you are using, sorry, not O of n, O of 1 only. Only a variable extra is there. Okay. So is everybody clear on this one? You
Yes, sir.
have a look at it again if you want to, right? You can have a look at the code again if you want to, right? Once you're clear on that, acknowledge me. We'll start with the better method. Okay. Okay, I think probably we can go ahead. Okay, probably we can go ahead now. Okay, so moving on to the second method, right? So the second method or the expected method is two-pointer technique. Two-pointer technique. Okay, two-pointer technique. See, in this approach, what will happen is the time complexity will reduce to O of n. We don't need a multiple loops there. We just need one loop which will do the entire job. Now let's see how we can solve this problem. Okay, let's see how we can solve this problem using two-pointer method. Okay, what happened? One second. I pasted something. Oh, chalo. I think I have to draw that image again now. Let me draw that image again. Okay. 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 So this is what it is. I think drawing this one. Okay. This is where the water is trapped. Okay. Now, so what we will do in this one is, let me highlight these things. Next time what I'll do is I'll keep these images ready so that we can save some time. Okay. So let's start with this. What exactly we will be doing, we will observe here in the two-pointer technique. So everybody can understand what exactly is a two-pointer, right, technique, right? See, this approach is based on certain facts. Let's start with that. What exactly they are? Let's observe that. Okay. The first one, if we consider a sub array, right? Sub array from where to where? Left to right. Okay. If we consider a sub array from left to right, we can decide amount of water either for ARR of left or ARR of right. Right? I'll show you the pictorially as well. Right? If we know the left max and right max, means left max means right, biggest element from, right, max element from, or for index 0 to left minus 1. Similarly, max element for right max means, just paste it here. That is max element starting from, okay, right plus 1 till last element, n minus 1. If we know these two facts, right, if we know the biggest element, right, or the maximum element for the left and right, then we can easily find out how much of water can be trapped there easily, either for the left or for the right, for anyone. Okay, if max left or left max is less than the right max, then we can decide for ARR of left. ARR, we can decide for ARR of left, else we can decide for ARR of right. Okay. So whichever is based on whichever is smaller, based on that we can decide it. In the earlier logic also we chose the smallest height. Similarly here also, whichever is the smallest, we can decide the amount of water that can be stored on either side, with for the left or for the right, based on whichever is the smallest value. Okay. Next, if we decide for ARR of left, is assuming that we are deciding it for ARR of left, then the amount of water, right, would be, right, left max minus ARR of left. And if we decide for ARR of right, then the amount of water would be, right, amount of water would be, right, right max minus ARR of right. So similar, it follows a similar method. Instead of individually doing it, we'll do it simultaneously, right? We'll do it simultaneously. Let's observe, right, with examples here. Okay. So we'll start working on it. Here, I need to mark some things here. Okay. Okay. So let's start from this index and this index. 1 second. See if I can move this. Okay. Where did it go? Large. Okay. So let's start from here. Okay. Let's start from here. Right. So first we need to, right, start from the left and right. Start from the left and right. So this will be my left and this would be my right. Right. So what we will do is right now we will assume left max as the current element. Okay. So I'll assume the left max has 3. Okay. Right max as 2. So right side maximum is this. Left side maximum so far or assumed in the beginning is 3. This one. This one. So we will assume that. Now what we will do is, right? And result is equal to what? Initially 0. So what is the first thing we will do here? Right? What is the first thing we will do is, right? You need to check the condition. If L max is smaller than R max, check the condition. If the L max is smaller than R max condition becomes false here. Right? Are you understanding?
Yes, sir.
Okay. So if L max, right, if L max is smaller than R max, then what we will do is we will add the, right, water to the result. So how we can add it here? Result plus, right, result plus, what is the R max right now? It is 2. 2 minus what is the current right? Current right is how much? It is 1. Current right is, it is 1. So 2 minus 1 is greater than 0. Right? If it is true, the difference between the R max minus the rightmost value, if it is bigger than 0, right, then what we will do? Question mark. We will assign 2 minus 1, right, this value, else we will assign it as 0. Right? Add the water for the right. So currently the L max is how much? L max is 3. 3 less than 2. condition fails here. If the condition fails, currently result is 0, right? So if the condition fails, that means we are deciding it for the right side, right? We are trying to decide it for the right side. So 2 minus 1, R max is 2, 2 minus 1 is the current, current value is 0. Current value is 0. Current element right side value is 0. So 2 minus 0 greater than 0. Yes, it is true. And 2 will be added. This will be added to result. So 0 plus 2, result gets added. So what I'm trying to say here is, right, you are able to predict the amount of water that can be stored for the right side, right? For the right side. So how are we deciding here for the right side? I'll repeat again, just observe. Okay. Now, initially, we did was we started for this right and left, and we assumed L max and R max. So left side for maximum element on the left side will be obviously border element, and maximum element for the right side will be the border element. Now we will assume, we will compare these two at the same time. Here, if L max, okay, is smaller than R max, we will compare them. So whichever is smaller, we can decide it for that element. If this condition fails, then we can decide for the right. If condition is true, we can decide it for the left. Right? In short, we are assuming the smallest element, whichever is smallest element, R max or L max, whichever is smallest, for that index, we can find the water that gets accumulated. How do we find it? You need to find it like this, right? So you need to check if R max minus current element, right side current element, ARR of right. So is greater than 0 or not? If it is greater than 0, add this element, means if it becomes greater than 0, that means if it is a positive number, then only water can be accumulated at that place. If it is negative, that means, right, you cannot accumulate water. How do you identify if it is negative? If this value is, right, if this value is, right, smaller than this element, right, if this value is smaller than current element, then we cannot store water because it will overflow. It will overflow. Or for example, just I'm switching from another element, switching to another element. Assume this is R max. Sorry, this is the right. Okay, this is the right. Now, which is the biggest element on this side? Right? So far as this. Okay. Now, what will happen here? Can I store a water at this place? I cannot store a water at this place. Right? Correct.
Yes, sir.
R max will be 2. Biggest element on the right side is what? 2. Minus current element. 2 minus 4 is minus 2. So if the element comes as negative, you cannot store a value because there are no bigger, bigger pillars are not there on the right side. You cannot store water, right? So based on this fact, we are generating the solution, right? So if this you get as a positive number, you will add this to the RES is equal to RES plus R max minus ARR of right. ARR of right. Else, if condition fails, you will add RES is equal to RES plus 0. Once you do that, you need to update the R max. Every time you calculate this, update the R max. Update R max. Did you understand, all of you, did you understand how to find the water accumulated on the right side? Can you drop me a message? Okay, good. Now what we will do is we'll directly go with the implementation and I'll show you how this can be done. Okay, we'll go for direct implementation. We'll remove all this data. Okay, so currently rainwater, we'll go with a two-pointer technique. Okay, we'll go with a two-pointer technique. So one variable is required for calculating the result. Okay, another one is right. One second, I'll just change these things. Okay, this is what it is. Now what I'll do is I'll initialize, right? Left is equal to index 1, comma, right is equal to index n minus 2. So these are the two pointers. These are the two pointers. So we are starting from these two places. We are starting from these two indexes. Okay. So I'm initializing these two pointers from the second element. Okay. And the last but one element. Next is I need two variables, R max, right, is equal to what we will assume right side maximum. We will assume, one second, we will assume this as a this element, last element as a maximum element, right side maximum. We will assume it R max. How do I get that? One second. How do I get that? ARR of right plus 1, right? So currently the index is right plus 1 index means we will get this value. Okay, and similarly for L max, int L max is equal to ARR of left minus 1. So for this one, what we did? For this one, what we did? We assumed this element as a left max. Okay, we assumed that as a left max. Next is what here? Next is traversing. Okay, how long, right, we should keep on traversing, right? While left is, when it is a two-pointer technique, right, both will collide at same place. Left and right will collide at the same place. Okay, so as long as left is, right, as long as left is smaller than is equal to right, we should keep on doing it. Why I'm taking is equal to? Because less than or equal to, because we need to calculate it for the middle element also. We need to calculate it for the middle element. If we are skipping that element, then we would write left less than right. Since we have to calculate accumulated, water accumulated at the middle element also, that is the reason we have to write left less than or equal to right. So what is the first step here? First step, what is here? If R max is smaller, right? So let's check if R max is smaller than or equal to L max. Okay. In that case, what we have to do? I can decide for the right side, right? I can decide it for the right side if condition is true. If R max is smaller, I can decide it for the right side. So RES is equal to RES plus, okay, R max minus current right element. If it is greater than 0, then if it is greater than 0, then add R max minus this element, R max minus ARR of right to the RES, else add 0. If you want, I'll give some space so that you can understand here. Okay, this, see, if R max is smaller, then check R max minus current element is greater than 0. Then you can calculate the water accumulated for the right, what do you call, pillar or a right pointer. Okay. Once you do that, you need to update right pointer as well. you need to update the right pointer. Right pointer, how do you update? Right is equal to right minus 1. It will go to the next element from the right side. It will go to the next element from the right side. Okay. So let me show you. Once you calculate for this element, now the pointer will move to this place. Right? So similarly, the pointer keeps on moving like that. Or else what you can do is you can simply write right minus minus. Okay. So you have to do this if the condition is true. And also we need to update the right max. We need to update the right max. So how do we update right max? R max is equal to, right? R max is greater than current right element. Current right element. If it is true, then R max will be stored as updated one because the value remains same, right? Else, you need to change the R max, whichever is the biggest one. So here what you're doing is updating R max. For the next element, R max might change, right? R max might change for the next element. So we need to update that R max. Okay. Okay. So this is what is for the right pointer. Now else, if the condition fails, then we can decide it for the left one. So else what we have to do, RES is equal to RES plus, compare it now, L max minus current left element. If it is greater than 0, then assign this as the water accumulated. This is how we calculate it. Okay. Else assign 0. Same reason on the left side also. After that, increment the pointer, left pointer, then update L max. Update L max. L max is equal to, if L max is greater than ARR of left, right? Then keep it as it is, L max, else change it to the left element, whichever is bigger, you assume that, right? Okay. So we updated the left. Once you come out of this loop, what you can do is you can return, right? Return RES. So are you able to understand this part? I'll just copy and paste this. Okay, let's go with only logical part so that you can see the whole thing in one. Oh, one second, I'm just trying to put it in one page. Yes, here it is. Here is the code.
Sir, in syntax in update LMAX, sir.
Where in update Lmax,
Yes, sir.
Lmax is equal to, sorry, syntax error. This should be greater than. So if Lmax is greater than ARR of left, keep Lmax as it is. Otherwise, update the Lmax to the left element. This was the syntax error. I'll correct it here also. Tendency of typing. When you work on multiple languages, this is what happens. Stored water is 0. Let's see where we made a mistake. Okay. Now, are we updating the Rmax correctly? If Rmax is, this is greater, then update that. Okay. Right pointer is getting decremented. else add the water for the left element. So else L max minus ARR of left is greater than 0. Somewhere some problems occurring. I think it's a priority. Priority, I think. Is it affecting? See, it told you priority. See, what was happening here is, okay, I'll just show you. See, I wrote it as RES is equal to RES plus. Okay, what was happening is this plus operator is having higher priority than ternary operator. So first this addition was happening. This addition was happening. So if you want it has to work in the same way, you need to put a brackets here for this and for this entire thing. If you put it that way, then it will work. I'll show you. RES plus, put entire thing inside a bracket, then it will work. It's a priority of operators. See, it is working now. Are you able to understand this code? Here
Yes,
I'll
sir.
keep it plus is equal to So this is what is the logic. So based on the two factors that we discussed here, the facts, see, you read it again, you will get it, right? If we consider a sub-array from left to right, so wherever the two pointers are there, we can decide the amount of water either for left or the right, right? If we know the left max or right max. And how are we deciding? If left max is smaller, we can decide it for the left. And if the right max is smaller, then we can decide it for the right. So how do we decide the amount of water, right? The amount of water can be decided as if left max minus the current element, left element is greater than 0, then water can be accumulated. If it is a negative value, then water cannot be stored. Similarly for the right as well. So this is all about, right, trapping rainwater. Now, is it, and by the way, any batch students can attend this training. Okay, I'll just download this file and if possible, I'll share it right away. Okay, I'll just download this file. One second. I have to put that code as well, right? Where is that? Yes. Okay, I'll just put that code as well here and share this file to all of you right now in the class itself. So we don't have to worry about it later. Just give me a minute. I'll just find a way to share it to all of you. More. I think we are not sharing a file is there. It is taking a lot of time to do this. We'll wait. And by the way, does the session which you are attending, is it helping you out to understand the things better?
Yes, sir.
Okay. So in the next week, what we will do is, right, in the next week, we will go with bitwise algorithm, basic operations. See, these are basic operation does not mean that we will teach you what is bitwise and what is bitwise or no. That is only for 5 to 10 minutes. Now you need to understand certain operations which are a tricky operation which we can do, right? Which we can do and perform the operations faster. Okay. So which will help you to kind of, you can say shortcuts. We call them as shortcuts or tricks, right? So that we will do it. What is happening? I don't know with this one. Just let me close this and reopen. So those tricks we will do it for one session. Probably it will require what you call around 1.5 hours or 2 hours. I'll give you certain examples also. Okay. Let me export this file, PDF file. Because I'm sharing this file right now because it becomes easy for everybody to collect it, those who have attended. Those who have not attended, that is not our headache. Correct? भाई जो क्लास बैठता है उसको बेनिफिट होना चाहिए. So just check everybody. Are you receiving the file or not? Yeah, uploaded. Check, did you receive the file or not? हेलो, मिला फाइल?
Yes, sir.
ठीक है, बढ़िया है. Okay, so we will meet again in the next week. Okay, we will go with all the tricks and shortcuts which are associated with bitwise operators. We will learn them and we will solve certain examples also. Okay, chalo then. Thank you for being in the session and attending it today. Take care, all of you. Take care, all of you. Bye bye. Have a great weekend. Okay, bye.
Thank you, sir.
Welcome. Bye bye. Happy weekend. Bye bye. I'm going to disconnect the session now.